All right, why don't we get started? Okay, so as the announcement says, I will be running the AutoGrader tomorrow night, midnight. And that means anybody who has turned in Project One, a version of Project One, doesn't have to be your final version. Anyone who's turned in a version of Project One will get it run. And you'll get a chance to check out for sanity checks, sanity and all that sort of business. Now, I suggest that you make sure that it compiles on the instructional machines before you submit it, otherwise you will have wasted a run. And by compile, I mean that GMake is supposed to work on it. You should also make sure that if you have private little things that you've added to your, that you're depending on in your makefile, that you've added to your directory someplace, to random places in your directory and put on your path, these are not going to be there when the instructional machine runs, so you better prepare to put them up there to make sure they get into the makefile or whatever manually so that they will get run properly. And of course that your directory is, that any such public things in your directory are properly protected. However, I would actually suggest instead that you just submit everything, make sure that you submit everything in your directory. One way to do this would be for one partner perhaps to sort of check things out at some random location and see whether GMake runs on it bare. And that would be a useful thing to do. You should check out, in other words, go to some random directory, maybe somewhere in temp even, check out a copy of your project submission. That is, check out my repo or my team or team repos /tag/proj1-whatever and make sure that that compiles. One thing that this will do is it will make sure that you have actually included all of the necessary files in your under version control. Because obviously if you don't, then they won't get checked out. Since everything is getting submitted through Subversion, they won't get checked out and we won't see them and your compilation will fail. So just take these simple little precautions. They're a good idea to do anyway. And of course, make sure, use SVN status and so forth liberally to make sure that you have actually managed to turn things in. If SVN refuses to commit something, then you can't just shrug it off and say, oh, well, I guess just things aren't working today. You lose. I mean, you haven't submitted it. I don't care what the reason is, you haven't submitted it. So overcome the bad habits that generations of CS164 students in the past have had and do it right. So there is a backlog of bug submits that I'm working my way through gradually. So have a little patience. There was one request for Flex 2535. Is that team here? 2535, latest version of Flex. Well, gosh, if that's where they're going to be. I think I'm going to install it in an alternative location, but you'll have to modify the makefile if you want to make use of it. Apparently, somebody wanted to use the -+ feature of Flex, which produces a C++ file. I had avoided doing that in this project because it's unnecessary, but they wanted to do it, and unfortunately, it makes more politically correct C++, I think. And unfortunately, that doesn't work with the version on the instructional machine. So, okay. What else? Yeah, that's it. And of course, there is a, I haven't mentioned it up here, but next week, as you know, on Wednesday next week, there is a test. So I'll be talking to the TAs about what kind of review. We've sort of gotten turned off by review sessions because what happens is the TAs come and just sort of find that nobody has any questions, so they just lecture, and that's pointless for a review session. So we'll work out something probably in the way of extended office hours or that sort of thing. Okay, administrative questions or anything like that. I'm glad to see that some of you are still coming to lecture. That's good. Oh, and two other things about the project. This is something that you probably should have started doing early when you were doing the project, but I have seen a few bug submits that are almost completely unreadable. I mean, the code is unreadable. Now, I don't know what it is that makes people think that they can have a line 360 characters long without white space in it and read it. But some people are actually doing that, it looks like, and don't, you know? Don't. Armando Fox was talking about this CEO of a small company whose interview style is that he sits down with candidates and pair programs with them. And if you were to do something like that, if you were to try to pull something like that in his presence, well, you'd be out on the street. So just think of it as a survival skill. Okay. All right. Let's see. This is not where we are. We are here. We're someplace else. We're over here. Yes, there we go. All right. So we were talking about. This is a concept, a general concept in programming languages that you have encountered in CS61A. And the concept is scope, which, just a quick review, is the region of text where a certain declaration has its effect. So in most of the languages that we deal with, this is defined textually. That is to say, this text in the program, the declaration applies in this particular text in the program. It is also possible, by means of dynamic scoping, to have cases where the declaration that applies depends on how you get to a certain point in the program. But although we talk about that and ask you for examples, we don't in fact actually use it if we can help it. And finally, this notion of a declarative region, which is basically sections of text or program execution that are defined to sort of be the fences around scopes. So a scope will typically be delimited on one end or the other by a declarative region. And we'll see what all of these mean when we apply them to individual programming languages. So, and again, you're allowed to one of the things that you get with scope and that comes out of this is that you can have multiple definitions of the same name, and depending on where they are, they mean different things. And this is somewhat controversial, actually, this property. For example, there are a number of languages, like Java, where you are not allowed to redeclare something inside a variable inside the scope of that variable, a local variable inside the scope of that variable, on the grounds that this would be confusing. But other languages have allowed it in the past. So, and the other thing is that you can sometimes differentiate names by the fact that they're used for different things. So I asked you for an example from last time in Java and C++. Can you think of an example where you can have two different things visible at the same point in the program with the same name, but there's no confusion between them? Two entirely different things, visible and nameable by the same name, even though they are, there is no ambiguity in their use. Does anyone know of an example of that? Yeah. Pardon me? No, that's, well, I'm sorry. Yes, function that's right. Function overloading is one example, but that's kind of obvious. How about an example from C where there is no overloading? Yeah.
You can have like a variable named loop and also a function named loop.
No, in those cases, in C, those would conflict. But you're sort of on the right track. You can have a variable named foo and a
method or a function?
no. Functions and variables in C will overlap each other. Well, in C++, you're right. In C++, it's a different. No, not C++. In Java, it's a different matter. Interestingly enough, but not here. Can you think? Anyone? Yes. Pardon me? Yes, almost. You can actually have a struct name and a variable name. So in C++, I can say struct foo squiggle. You can say that in Java, you can only say class foo, but in C and C, you can say struct foo squiggle, and foo can be reused for other purposes. It's very confusing, but you can do that. Another example from Java is constructors. You can have a function named foo and a constructor foo in the class foo. This, however, is considered very bad practice for obvious reasons. So now the reason that you're allowed to do this is that the context in which these things are used is distinctive, so they can tell them apart. So, for example, with constructors, you say you only invoke the constructor after the keyword new, so that's unambiguous. Whereas functions, you don't put them after new, so that isn't. Okay, so that's an example of the way these things can sometimes work. And you are all familiar, I think, with this rule, the so-called, I call it the Algol scope rule, the block structured syntax rule, namely that the scope of a declaration begins somewhere, begins at the declaration, or sometimes at the beginning of the declarative region that includes it, and goes up to the end. And where there's overlap, the innermost declaration prevails. So if you have a block nested inside another block and both define the same variable, then in the inner block, the inner declaration prevails. But as I said, there's some languages say, oh, this is confusing, so for the benefit of the program, we won't allow it. Okay, so here's the sort of thing that means, here's the sort of thing that we're talking about with declarative regions. In Java, if you have a variable declaration of any kind that's inside curly braces, which could be a class or what have you, then the declarative region ends with that curly brace. The curly brace marks the end of a declarative region. In other words, it marks the end of the place where declarations have any effect. This is in contrast, if you look at things like Python, for example, or at least Python 2.5, I think they're modifying it in 3. In Python 2.5, you have this interesting phenomenon, which is that there aren't inner blocks, really. That is to say, if you define a local variable anywhere inside, if you assign to a local variable anywhere inside Python, a Python procedure, the scope of that variable is the entire procedure. We say the entire function. We say that the declarative regions are the suites, the indented portions. No, I'm sorry, they're not the indented portions. They are the indented portions of functions. That's why, by the way, in our syntax, in our abstract syntax, I distinguished between blocks and other lists of statements. A block is a list of statements that is also a declarative region. So in Python, this statement here, for example, after this statement, x is defined. And x is defined to be actually 10 at the end of that statement. So the fact that I have this construct in here does not introduce this is not a new declaration of x. There is just one x in this whole thing. So So each function, so in Java, each function body is a declarative region. What would you say are other declarative regions in Java? Oh, come now. You've all spent hours slaving over hot terminals writing Java, so you should know this, I think. Declarative regions in Java. In other words, hook up my blather with what you know, and thus demonstrate your understanding. I saw just one hand. Okay.
Besides class one.
Classes, besides which?
Besides class one, class declaration.
What's wrong with that? Yeah, that's a perfectly good example.
Yeah.
Yeah.
An obvious one. Then inside like a while for.
Oh yes. Okay. Well, not while, but for the for statement in Java can introduce a new variable. You can say for parenthesis int x, and that variable has the is scoped to the end of the for statement. Yes, that's right. Anything else? Yeah. No, that's not a. I mean, if else does not by itself declare a new declarative region. You can have squiggly braces inside there, which define blocks, and the squiggly braces give you declarative regions. But an if or else without squiggly braces is not in and of itself a new, doesn't delimit declarations. At least not usually. Yes. Yes, switch statements are an example. So it's kind of confusing. It's generally discouraged to declare variables in switch statements unless you put them inside, enclose them in further squiggly braces. But yes, you can do that. Okay, so these are all examples. Now basically what I'm doing here is I'm going through these words and showing variations among programming languages. Here is a variation that's kind of interesting. So I declare a variable. Now the question is, what is the status of that variable just before the declaration? Now in a number of languages, such as, for example, C for the most part, Ada is another one. The idea is that the scope of a declaration in general starts with the declaration and ends at whatever the end of the declarative region is. So, for example, you have a variable, you have int x equals, or int x semicolon somewhere, and that goes up to the next closing squiggly brace, or next nested squiggly, or the squiggly brace that ends whatever block you're in. But you also know that in Java and C++, there are these funny things where you can declare something like the field of a class or a method, and somehow magically that method or field name is known even before its declaration. So you know this. I mean, if you can put all of your field names, all of your instance variables down at the end of your class declaration and still refer to them up above. And that's not all. There's also this funny thing that in Java, when you write a class someplace, its name is available everywhere in the same package. It's just sort of floating out there. So even when you have two classes that refer to each other, they're mutually recursive, that works, even though there can't be any order in which all the declarations from one precede all the uses in the other. So this is a choice that you can make, that the language designer has in how to design a language, and depending on the language, they might come up with different solutions. So in C, the problem is that in C, for example, you still need to have mutual recursive definitions of things. So you might have two functions that each call each other. So what do you do in C to get around that, or C++? Do you know? I have two declarations. I have two functions. Each one of them calls the other. Both of them call each other, I should say. But I have this rule that says I have to declare things before I use them. So what happens? Yeah, in the back there. Yeah. So in C, there's a distinction between declaring something and defining it. So you can declare a function, which means that you give everything except its body. Those are the extern declarations, or sometimes static declarations that you'll see in header files. And you can define something, which means to give it a body or a value. And by judicious use of these, you can form basically the declarations are promises that eventually something will be defined. And then, as somebody mentioned, we have overloading, which is another way that two names can refer to the same thing. This is an idea, well, this is basically the idea here is one of expressiveness. You have two activities, both of which are reasonably called adding something, but obviously what they mean depend very much on what kind of thing you're adding to. So, and it's and you can do what C does, which is that you invent new names. You say add, you have add to set, or add set, or set add, or set add, list add, etc. That kind of thing. You can use that. You can use prefixes. You can use or some sort of module thing like a namespace or some such thing. Or you can simply say, okay, fine, I'll let you use the same name, and you just have to use and you just have to differentiate on the basis of what are the argument types, for example. So here we have an example of two add routines, one of which works on integers, one of which works on floats. And the compiler decides on the basis of the types of the arguments which to use. That's overloading of the name, or sometimes ad hoc, sometimes called ad hoc polymorphism. And now in C or C++, the return type is ignored for this purpose. So if I had two routines, both of which had the same argument types and returned two different types, like down here, you'd get an error. You'd get an error. You'd be told that this is ambiguous, that your call is ambiguous. Whereas there is one language that I know of. Well, actually, I take that back. There is one language I know of that does this extensively, and that's Ada, where in fact the return type and the argument types both matter in deciding how to resolve overloading, and that's kind of useful. You may have run into the case where you want to define a function like empty list. Well, empty list of what? How do you know? And or something like, define something called empty, let's say, which will, an empty what? An empty set, an empty list, what is this? And in a language where you differentiate on the basis of return type, you can sometimes just write that and it all works because the language knows, oh, you're assigning this to a set, so it must be an empty set. Now in C++, does anyone happen, I'll bet you don't, but I'll ask it anyway. There is a place in C++ where they choose on the basis of return type. One place. It's a complete anomaly. So much of an anomaly that, of course, you don't. All right, I'll give a penny to whoever finds out what it is. Huh? No, not really. I mean, type conversion on assignment is I mean, if you do x equals f of something, then the type of x generally has no effect on the f that you choose there. But there is one case where something strange happens. Well, okay, I'll leave that to you. Now there is dynamic scoping, which you may have heard of. Brian Harvey, for example, is rather fond of this. because like me, he comes from the old days when these languages were current. Lisp is still current, but APL and Snowball, APL maybe to a certain extent, and Snowball to the aficionado. Snowball was a string manipulating language, a really interesting string manipulating language, especially in some of its faster implementations. It could beat Perl and so forth all hollow when it came to regular expressions. Well, so the idea here is that we look at the most recently executed and still active declaration of a variable. Still active means we still have a notion of declarative region. It's just that when execution leaves a declarative region, the variable disappears, rather than when you're outside the text of a declarative region, the variable disappears. So here's an example of, well, this is C, which does not use dynamic scoping, but this is a what if. Suppose we lived in a world where C was dynamically scoped. Then this declaration, this statement here is illegal because there are probably several reasons why it's illegal. Assuming that print is defined someplace. What is wrong with this? Kind of obvious. Yeah. X isn't defined in G. But if we have dynamic scoping, then the rule is, well, when you see this X, we say, oh, well, how did we get here? If we got here by calling F1, then you see there's a declaration of X in F1. And so we declare X. It's still, when we call G, or while we are executing G, that declaration is still there because we haven't reached the closed curly on F1. So we execute and print 10. And then when the program calls F2, the thing will go in and print, the first thing we do is we call F3, which declares the variable X to be 30.5, but then reaches its right closed curly, and so that declaration goes away, and we're left with the declaration of string X equals hello, which is then what gets printed. So that's what dynamic scoping is. Now this can sometimes be actually rather useful. I say original Lisp. There are actually other Lisps that do this. For example, eLisp, the Lisp in Emacs uses dynamic scoping, and that allows a very interesting little trick because you've got all of these. They have all of these global variables that hold settings of various options and things like that. If you want to temporarily change the value of one of those variables and then set it back to its default value, a very nice trick is to let's say it, call it idiomatic trick, is to simply have a let that gives the new value to the variable, execute whatever you want, and then when you leave, the old value is automatically restored. It's really kind of neat. But this is not a feature that's particularly popular among language designers because, especially among compiler writers, because of point 2 there, which is that it basically the poor compiler writer looks at a use of X and has absolutely no idea where this came from or what it's going to be. That isn't going to be determined until runtime, so there's not much you can do except generate very general and presumably slow code for it. So that's another dimension in our landscape of possible scoping rules. Now here's another one that you see variations on. And the question is, am I required to actually write out a declaration, or does the language allow my declarations to be implicit? So you have the older languages in particular tended to go in for implicit declarations, and that was because at the outset of at the dawn of the programming era, people thought of type declarations as a nuisance. I shouldn't have to do this. In mathematics, I I don't say x int. I say, you know, let x be the upper bound of the, or let x be the set of the subset of n, such that n is even, or something like that, such that x is even, and you can tell that that has to be a set of integers. But the only reason these declarations were put in was for the benefit of the compiler writers, so that they could generate good code. But then people found uses for that, sort of mission creep, if you will. They found uses for these declarations, like it makes your program clearer, for example. It catches errors. You still see some of the old school in C, where if you write a call of a function, if you write foo paren 3 end paren, especially in old C, it'll say, oh, this must be a function, I can tell because of the parentheses. So I have no idea what argument types it takes or anything like that, so I'll just guess that it's a function that takes any number of arguments. And I don't know what its return type is, so I'll just guess that it's returning an integer. Now this may seem strange, but that's the way I mean, they actually, to the point that they actually had to write a separate program called lint to go through all of your code and make sure that you use this consistently. You will still see traces of lint. I think it's obsolete, but some people, I think, still use it. Now Python, because Python is dynamically scoped anyway and dynamically typed anyway, there's no point in all you would be doing declaring a variable is you do what you do in JavaScript. You say var variable name. Well, heck with that. We'll just have this rule that that when you assign to something, it becomes a local variable. That's how they decided to do it. Fortran was the old school, so it decided what type something was by the first character, which was some sort of compromise. So you didn't have to, since mathematicians usually use things like I and J and K for indices which would be integers, and X and A and B and so forth, real numbers, they just decided to make that convention. But the point here is that even though it doesn't look like there's a declaration, there is. The compiler knows that something has been introduced because of these implicit rules. And so it's not fooled. It put these in. Well, I should also say that there is a modern trend in, as we'll see actually, in languages like ML, where you don't have to write the type because the compiler can figure it out. All right, so the idea here is that we are going to, hang on, let me see how many, where am I here? I am, because it's getting kind of late here. Oops, wrong place. I am explicit, okay, so we're almost there. All right, let's finish this up. So the idea here, I said that last time that the goal of this semantic analysis for at least in this course, is to garner certain information and decorate this nice tree that we've generated with a bit of extra information. So the question is, how do we do that? And the answer is, as usual, you saw it in 61A. You thought you were going to escape from these, didn't you? Well, I'm afraid not. Environment diagrams, here again. So you remember this. You call something, you call something like f, and what happens is you end up with this linked bunch of mappings from variable names to values. So you have the global environment that contains definitions of x and f, or values of x and f. You have the declaration of f, the body of f, which contains the declaration of x, and then you have the body of the let statement that contains the declaration of y. And whenever you want to look something up, you just start at the pointer that says current environment and work your way back until you find one that contains the variable name you're looking up, and that value is the one you want. So you remember this, right? Now, suppose that I just take away those values and I replace them with abstractions, with something more abstract. I'll just say there's an x, and I give it some extra information, like, for example, maybe it's type. I'll just tell you that there's an x and it's of some type, an f of there is some type, and so forth, and we can build these up. And this data structure that results, a block-structured symbol table, is basically something that a compiler can use, because basically the compiler can go through and it can say, just as you can say, well, the point being that this diagram here, the values you may not be able to know until runtime, but the structure of this diagram is fixed by the text of the programming scheme. And likewise, in any statically scoped language, such as the ones that we're dealing with. So we can use exactly the same structure conceptually and just substitute abstract information for the concrete values that go in there. And that's basically the idea. So with this data structure, we can handle symbol tables. We can handle the mapping between, or a compiler can handle the mapping between variable names and what they mean. It can use this to keep track. So as it goes through the program, as you traverse through the program, you just sort of abstractly interpret it and build up a structure like this, except that you have to substitute abstractions for the values. There you are. As I say, as is so often the case, everything you need to know in a course you've already learned in CS61A. Right? So on that discouraging note, why don't we take a little break, unless there's a specific question? Okay, let's take a little break, and then I'm not sure what I'll do, but I'll probably maybe start on new material, or if you have questions about the project, you might also think to ask those.
You got a question?
Yes.
Somebody had their hand up.
Oh, I'm sorry. There's one in every crowd, isn't there? See, end of let, end of define. Oh yes, you're right. I'm missing a parenthesis after the in the Y group. No, I'm not. Wait a minute. Yes, I am. That's right. I'm missing a parenthesis in the left. So, good. Thank you. I will fix that.
I was just going to say, is the return type in classes where you're overloading the equals operator?
Uh-huh.
Yeah.
What's this? The return?
No. It's the question you were asking earlier about the return type mattering.
Oh, I see.
Is that in the overloading of the equals operator in a class? You can see the return. You can see the type of the one on the left and the type of the one on the right.
Yeah, but you'll find here. You'll find that doesn't make any difference. So if I have, for example, if I have an f that returns int, and I have an f that returns maybe char star, all right, and I say int, so these are two functions, and I say int z equals f, the compiler will complain. It will say, I don't know what this is. I don't know whether it's this one or this one. It's ambiguous. And my question is there a case where the compiler doesn't do that, where it says, okay, I can figure that out?
But if this is a function or if this is a class? If it's a class constructor, isn't there a way to have it know?
If there's a class constructor, then you can't overload it. You can't have two. Oh, I see. You can't have two classes with the same name. Now, if it's a class, oh, I see. So you say something like this. Well, but that would require that you have two constructors for f. But all constructors for f return the same. All constructors in the class return the same type.
Oh, that's right. You can't make it.
Yeah, it doesn't work that way. It's really obscure. Believe me, it's really obscure.
I think I found it on the internet. So is it like overloading the int or like or whatever operators in the class?
Overloading the operator int.
So like you could have a function that returns a class, and they have operator int and like operator like.
Oh yes, I see. Yes, the coercion operators. Yes. That's actually. Oh, actually, that's. Yeah, that's actually one of them. There's another one actually. But yeah, that's right. That's good. Yep, that would do it. So the coercion that you apply depends on context. That's true. Mm-hmm. So you can have this is operator and then type here. And I don't know if you've ever used this, but it's the rules are complicated. There are these preference rules for which ones you use in preference to whichever the ones, and this complicates them. But it is kind of handy sometimes. There is another case though. That's good. So that's one case. Good. I'll bring a penny next time.
Did you see the post about the PyOnParse possible bug?
A post? No, I don't. I mean, I didn't see bug submits about PyOnParse. So did it have to do with def? I think I fixed that.
Oh, in 0.13 or?
In 0.1. No, it's PyOnParse. No, I think have you tried it on the instructional machines today? Pardon me?
I haven't.
You haven't? Okay, well try it and see. Yeah.
Is it possible to get solutions for the past midterms?
To get which?
The solutions for the past midterms?
Well, where's the fun in that? All right, I'll post something. Yeah, I don't like to make those. I don't like to let those circulate. But okay. All right. All right. Questions? Project related or otherwise? Please, if I know that we have a large backlog of bug submits, but nevertheless, please, in the welter of comments and things that get put on the Piazza bulletin board, complaints about the software not working tend to get lost because somebody responds. Somebody responds and says, "Yeah, that happened to me too," and thereupon it's no longer an unanswered message. So remember this, and please use bug submits for all of these things. Just send us a test case. This doesn't work. Here's how you here are all the files that you'll need to reproduce the error. Here are the commands you need to reproduce the error, and we'll take it from there. But please do that. Please do it that way. Otherwise, things are likely to fall through the cracks. I'll just say a few words. We only have a few minutes, but we'll at least get started on this topic. So we talked about one of two main things that type checking does, and the other one, that the static semantics does, static semantic analysis, which is determine what names mean or what declarations refer to them. And the other thing is this thing called types. So I haven't actually said what a type is. The classical definition is that a type is a set of values and a set of operations on those values. That's the classical definition. So what you're trying to do is determine what are the possible sets of values for each of these variables in the program, or each expression in general, each expression in the program. And one use of this from the point of view of the programmer is that you can find errors before having to execute the program. Now, there's a big debate these days about this. I don't know if it's a big debate, but somewhat of a debate. there is the new school of scripting language people, like the folks, the Ruby on Rails folks and so forth, who have dynamically typed languages. And they've made a virtue of necessity, and they've proclaimed the new, this new era of, this new doctrine of duck typing, D-U-C-K typing. This is from the old saying, if it walks like a duck and quacks like a duck, it's a duck. So what the idea is that if your program, if you have some object that responds to the message, print yourself, then and you give it any kind of anything of any type that prints itself when asked to print itself, then you have your program is correct. So your whatever it is, it walks like a printable thing, and it talks like a printable thing, so it must be a printable thing. Needless to say, the old school a lot of people tend to think this is crazy, especially for large programs, and that debate continues. So in any case, whatever the language, whether it be dynamic or static, there will be these type rules that determine either at compile time, either statically or dynamically, what the types of all various expressions are and various results are. So type errors, what sorts of errors can you think of that might fall in this category of the compiler noticing that the type of something is wrong for its particular use? Where does that come up? I see the usual hand, 2 usual hands, 3 usual hands now. Oh, come on. You're trying to tell me that this whole class, nobody has ever seen a type error in their program when they run the compiler? And so you have no idea what I'm talking about? Oh, come on. You can't be that good. I've seen your code. Oh, come on, just a guess. Anybody. Somebody who hasn't spoken before. You, for example. What would you, they'll teach you to sit in the front. What would you say as an example? What's an example of a type error? Yes, an assignment, a wrong assignment. See, he knows the answer. I mean, why haven't I don't know what this is. I see you. Is it fear that your classmates will start to think that you're know-it-alls if you answer questions in class? Is that it? Well, don't pay any attention to them. Pay attention to me if you're going to fear anyone in this classroom. All right. Okay, so assignment statements. Anything else? Another example? Yeah. Right. So operations. An operation, right? So operations can expect certain types, and if they don't see that, they get upset. Anything else? Another one. All right, fine. I'll call on you.
Some sort of function argument that doesn't.
Yes. So. Right. So yes, that's right. So function arguments. Function calls have to have things of the right type. So these are all examples of type errors. All right, well, we'll continue with this topic on Wednesday.